In this section, we're going to discuss a special kind of logarithm called a natural logarithm. And all that is a log that has a base e on it. So you're taking log base e of x. Well, they're going to give it a special notation. They're not going to write log base e, they're going to write ln of x. And ln means natural log, it's just backwards, ln, natural log. And it assumes a base of e automatically, kind of like log, when it has no base, assumes a base 10. Well, ln assumes a base of e. And so you don't need to rewrite it like this, but just know that that's what it equals. And so you'll have ln of x. And we write it with lowercase letters when we write it by hand, but on the calculator it is a capital L, capital N button on your calculator, and that already assumes base e. You don't have to put the base e in. What e is it's called the natural number or the natural base a lot of times, and it's an irrational number. I say approximately equal to because I've rounded it off to 2.718, but it actually goes on forever and ever with no repeating pattern, so it's an irrational number, and it always is given the letter e. So it's not a variable, it actually represents a specific number every time, and it's called the natural number. The reason it's called natural is because it occurs in nature a lot, and you'll actually see this number in science a lot, and so it has some special qualities to it. You'll also see this number in financial formulas a lot of times, and so you may have noticed when we did exponential functions that there was a PERT function, and that was continuously compounding interest, and there was an e there as well. So you'll see this letter from time to time, and it's kind of similar to how pi is a Greek letter that always represents approximately 3.14. That actually is an irrational number that goes on and on and on, but we round it to 3.14 a lot of times just for simplicity's sake. But pi always represents that number, and it doesn't vary. So e has similar properties to that. As far as how the graphs look, the ln function is an inverse function of the exponential function called e to the x. And so the exponential function of e to the x is roughly like this, kind of like all our exponential functions, and this would be exponential growth because e is a number greater than 1. It's 2 point something, so it's obviously greater than 1, so it's a growth function. So you know now that the inverse function of an exponential function is a log function, and the log function kind of has this general shape to it. And that would be the ln function as well, would have that general shape. And like we've said before, every inverse function is a reflection across this y equals x line. So those reflect across that line in the same way that logs do with their matching exponential function. So as long as the bases are the same with the exponential function and the log function, then those are considered inverse functions of one another when their bases match. Because ln is a log, it has all the same properties that all the other logs do, and so we can do things like write multiple logs as a single log, and so we can do things like the power rule where we can move something that's being multiplied in front of the log, we can put it as the exponent on the log. We can also take these two separate logs that are being subtracted and make it one log being divided. And if you work out 15 squared divided by 75, it actually comes out nice to ln 3. And so you could, if you needed a decimal approximation, you could put ln 3 in your calculator and see what decimal that makes. Or you can just sometimes leave the answer ln 3 if they want an exact answer that's not rounded off. So depending on which kind of answer they want, this would be an exact answer that hasn't been rounded off, and this would be a rounded off answer because it actually went on past the 6, but I rounded it off at 4 decimal places. So either one of those answers would be right, just depending on what the person wants who's asking the question. You can also solve equations that have ln as part of the equation, and you could solve for x in this case, and you use all the same properties again, maybe the definition of log where you change between log and exponential form. That would be useful here. So we're going to visualize that there's a base e there on that log, even though we didn't have to write that, but that helps us to see that you could rearrange this into an exponential function, e to the fourth power equals all that stuff. And so e to the fourth power equals x minus 3 squared. And one method to get this solved would be to square root both sides. If we square root both sides, let's see what we get. Square root this side, square root this side. Remember, you have to write a plus or minus sign on one side or the other, and you always write it on the opposite side of where the x is, and so your plus or minus sign has to go over here. And then the square undoes the square root, and you end up with x minus 3 equals plus or minus. Well, if we have 4 e's under here, and you picture how many pairs you have of e's, you'd have 2 pairs of e's that would all come out of the square root and nothing would be left in the square root, so that would be the next part of your answer. And then to finally solve for it, you could add 3 to both sides, and these would cancel and you'd get x equals, and you'd have 3 plus or minus e squared. If they wanted exact answers, you would leave e in the problem like this, and there would be 2 answers, 3 plus e squared, 3 minus e squared. Or if you put them in the calculator, you can get a rounded off decimal. The plus version gives you this one, the minus version gives you this one, and those are rounded off, and those would be possible answers as well, depending on what the directions are. Here's another type of equation that has e involved, and it also has x in the exponent, which, let's see what happens here. You want to get this part by itself, if possible, before you do anything else, and so we want to subtract 2, or add a negative 2. We also want to divide by 4. Then at this point there's a couple of ways you could go. You can either use the definition of log and rearrange this into logarithmic form. Another thing you can do is you could ln both sides to get e out of the exponent, so you can move it down in front. And at this point you can get x by itself by dividing out. You can divide out the 2 and the ln e at the same time if you would like. And this would cancel down to a 1, and this would cancel down to a 1, and you just end up with x equals whatever all this is in the calculator. So again, if you wanted a more exact answer, you could leave it with the ln's in it. If you wanted a rounded off answer, which is probably more likely, you could round it off to 0.626 approximately. And so that is just straight calculator work, putting it in just like it looks, except if there's ever more than one thing in the numerator or denominator, I would suggest putting parentheses so it understands that it's not just dividing by the 2, but it's dividing by the 2 with the ln e, all that's in the denominator, so that's probably a good idea to put parentheses around the numerator and denominator separately. I want to do one example of a word problem just so you can see in the real world how some of these formulas are used that have ln in them. This one is out of the Pearson Algebra 2 Common Core 2012 book, and it says a spacecraft can attain a stable orbit 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second. The formula for the rocket's maximum velocity, v, in kilometers per second is v equals negative 0.0098 t plus c ln r. The booster rocket fires for t seconds, and the velocity of the exhaust is c kilometers per second. The ratio of the mass of the rocket filled with fuel to its mass without fuel is r. That's the ratio of the mass of the rocket filled with fuel to its mass without fuel. Suppose the rocket shown in the photo has a mass ratio of 25, a firing time of 100 seconds, and an exhaust velocity as shown. Can the spacecraft attain a stable orbit 300 kilometers above the Earth? So as we can see, they give us the mass ratio of 25, so I wrote that over here, the firing time of 100 seconds, I wrote over there, and an exhaust velocity as shown. It's over on the side there, and it's 2.8. What we don't know is v, so let's use the formula they give us to find v. Filling in the values in the appropriate spaces, we have the t, the c, and the r, and then we can put that straight into the calculator just like it looks and see what we get. We get approximately 8, and if you look back up into the question, it says that v is measured in kilometers per second, so we put kilometers per second here. And the question is, can the spacecraft attain a stable orbit at 300 kilometers above the Earth? If you look back at the beginning of the question, it says a spacecraft can attain a stable orbit 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second, and it just reached one of 8 kilometers per second. So since that is greater than the 7.7, the answer is yes, it can attain a stable orbit 300 kilometers above the Earth.